Welcome to video tutorials for SILCS Bio. In this video, we will go over visualizing SILCS FragMaps. The information discussed in this video is also available on our documentation website, docs.silcsbio.com. There are 4 different options available to visualize SILCS FragMaps. By default, you can visualize your FragMaps in the SILCS Bio GUI. We also provide support for visualizing FragMaps in the popular molecular graphics softwares VMD, PyMol, and MOE, so that scientists can share their FragMaps with their colleagues. In this video, we'll take you through what SILCS FragMap files are and how you can use the SILCS Bio GUI to visualize and analyze them. For this tutorial, you will need your FragMaps directory and corresponding protein PDB file. After your SILCS simulations are completed and corresponding FragMaps are generated, you can find your FragMaps in a directory named SILCS_FragMaps_ your protein PDB prefix. So if your protein PDB file is 3fly.pdb, then your FragMaps will be in the directory SILCS_FragMaps_3fly. This directory will contain all of the files required to visualize your FragMaps. First, let's see what's in the SILCS FragMaps directory. Okay, so we have our protein PDB file and the corresponding FragMaps in the Maps directory. Now let's go into the Maps directory and we'll see that we have all these FragMaps files, one for each of the different FragMap types. Okay, back in the SILCS FragMaps directory, we see these plugins directory and these view maps, PML, and VMD files. These files can be used to visualize your FragMaps in PyMol with a PML file or VMD with a VMD file, but for this tutorial, we'll be focusing on using the SILCS Bio GUI for visualizing FragMaps. Now we'll go over how to open the GUI and how to load FragMaps. Okay, first we need to open our SILCS Bio GUI, and on the landing page, we'll click on Visualize SILCS FragMaps and Ligand Analysis. And here we can load our FragMaps protein or ligand file. Now let's click on Select FragMap Directory, and we have an option to look through our local computer or a remote server. For example, our files are in our local computer, so let's go back to Local and click on Open File Browser. And we can simply click and open our SILCS FragMaps directory we looked at earlier. And let's add a ligand file to look at as well through the same process. And once we have all our files loaded, we can click on Show to see the FragMaps protein and ligand. Next, we'll look at how to change the protein representation. Okay, so in our visualization window, we can see our protein is in the default cartoon representation. Let's hide these FragMaps to better see the protein, and we'll go to the Protein tab to change the protein representation. We can hide the protein altogether with Hide All, and we can turn on representations by selecting their checkboxes. So here's a surface representation, and we can turn the protein by clicking and dragging. We can move the cutting plane by holding down the Shift button and scrolling, and we can zoom in and out by scrolling. And to reset our view, we can click on the Zoom button. Okay, let's turn back on our cartoon representation and our other options to see the ball and stick representation and the protein label, which will ID each residue. We can also visualize any of the ions and van der Waals representation. And finally, to reset the protein view to the default settings, we can just click on Reset to Default. Now we'll look at how to load a ligand. One way to load the ligand is to directly load it at the same time you load your FragMaps and protein files. So I've loaded the crystal ligand for this protein, and we're going to click Show to open our files. Okay, so here we can see the nice overlap of the different FragMap types with the different functional groups of the ligand. And now in the Ligand tab, we can see that loading our ligand this way will not allow us to do any ligand analysis, and the LGFE is NA. To do ligand analysis, we can open the ligand file we get from SILCS-MC docking by clicking on Load Ligand and selecting the ligand we want. In this case, we're looking at the crystal ligand pose optimized to the FragMaps using SILCS-MC pose refinement. And now we can see its LGFE score. We can also hide and show our loaded ligands by clicking on their checkboxes. Now let's go to the protein tab and turn the protein off. And now we can see that the pose is essentially the same, but with minor shifts and rotations to maximize the overlap of the ligand with the FragMaps. Now let's look at how to toggle FragMaps on and off and adjust their GFE isocontour levels. Okay, so here are the default FragMap settings. And so here's the FragMaps, the protein, and the crystal ligand. Now let's go into the Ligand tab and zoom into the ligand. And let's also hide the protein cartoon representation. So now we have the generic apolar, donor, and acceptor maps on right now, and we can show more FragMaps by clicking on their checkboxes. And these show where these functional groups are favored to bind. Now we can also hide the newly shown maps by clicking Reset to Defaults. And we can also hide FragMaps by deselecting their checkboxes. So now we only have the generic apolar maps on, and these maps show where the apolar functional groups prefer to bind. We can also use a plus or minus here to adjust the GFE level. And so now we can see the apolar maps shrink, and any apolar atom within these maps have an atomic GFE of at least minus 1.8. Now the generic apolar map is based on benzene and propene probes in the SILCS simulations, and we can see how the aromatic ring of the ligand aligns with the benzene map, and the other apolar groups of the ligand align with the propene maps. Back to the generic apolar maps, let's increase the GFE level, and as I do this, we can see how the maps increase in size. And let's turn on the protein surface and find our ligand again. Now we can see how the generic apolar maps fill in the ligand binding pocket of the protein, and this can be used to see accessible pockets in the protein. Now we can return to our default settings by clicking Return to Defaults, and we can also hide all of our FragMaps by clicking Hide All. Now let's look at the exclusion map and how it compares to the protein structure. Okay, so here's our protein with its FragMaps, and let's go to the protein tab and show the protein surface. And if we go down the list of representations, we'll come across exclusion map. So this surface and every representation listed here besides the exclusion map corresponds to the initial structure or input structure used in the SILCS simulation of the protein. Now let's turn on this exclusion map, and now we can see that the surface of the protein completely covers the exclusion map and we can't see it. So turning off the surface, we can now see a tan exclusion map. Let's see how the exclusion map looks with respect to the crystal ligand. We can see based on the exclusion map, the binding pocket is very open. And compared to the exclusion map, the surface of the initial structure is also more compact. So in SILCS calculations, we use the exclusion map to account for the protein flexibility. The exclusion map shows where no probes of the water sampled in the SILCS simulation, and therefore shows regions of the protein that are completely inaccessible and accounts for protein flexibility. So compared to the surface structure, the exclusion map shows all of these pockets and regions that can open up. All right, let's get into how to analyze ligands in the SILCS BioGUI, starting with analyzing crystal ligand poses. So here's our FragMaps loaded with the crystal ligand, and in the ligand tab on the right-hand side, you can see it listed as 3FLY_ligand. Now let's click on the zoom to focus in on our ligand, and here's our ligand in the binding pocket. So let's clear our view a bit by hiding the protein representations. And we'll also focus on only one type of FragMap, so let's click Hide All and turn on the generic apolar maps. So adjusting the GFE levels to less favorable or more positive will typically give us an idea of the overall shape of the pocket, and changing the apolar FragMap level to highly favorable or more negative will show us regions that are highly hydrophobic and apolar in nature and are going to contribute significantly to the ligand scoring going forward. Now let's turn off the apolar map and turn on the generic hydrogen bond acceptor map, and let's decrease the GFE levels. And as you can see, the nitrogen atom, being a hydrogen bond acceptor of the ligand, overlaps nicely with the acceptor maps. Now with the hydrogen bond donor map, we see some favorable regions that are not well occupied by this ligand. With the hydroxyl oxygen map, we see where both H-bond donors and acceptors are favorable. So we can see some opportunities to add these functional groups to the ligand to further improve its LGFE. Lastly, let's look at the water-oxygen maps. We can see many regions around the ligand where water molecules are sampled favorably. And let's also visualize this in the context of the binding site proteins by turning on ball and stick. And so this will allow us to evaluate crystal waters and facilitates ligand optimization by replacing structural waters. Now we'll cover how to analyze ligand poses derived from SILCS MC pose refinement. Here we have the FragMaps loaded with the crystal ligand and the exclusion map turned on. Now let's go to the ligand tab, and we can see that our crystal ligand doesn't have any LGFE information yet. Let's go ahead and load a new ligand pose, which was generated by running SILCS MC pose refinement by clicking Load Ligand. And this can be either the SDF or PDB file output. And so here we're going to do the SDF file output. All right. So now note that this new ligand now has an LGFE score. Now, as you can see, the refined pose is different than the crystal pose. And now let's get a clear view by removing the protein representations to see the ligand more clearly. All right. So now we can analyze the ligand in the context of the binding pocket properties as we did previously, but now we can also do an atomic GFE analysis of the ligand. We can quickly recognize the differences between the ligand poses by turning the crystal pose on and off. Now let's focus on the SILCS MC refined pose and this apolar region to the right of the ligand, and let's hide the other FragMap types. Now by clicking on each atom, we can see their atomic GFE score. The sum of the atomic GFE scores results in the total LGFE score. So once we've selected all of our atoms of interest, we can go into the Ligand tab to the right and use the drop-down menu to select a ligand name. This will show the sum of atomic GFE scores for only the selected atoms, allowing you to know the overall contribution of a functional group or substructure to the total score. So this group contributes about -3 kcal per mole out of the total -8.4 kcal per mole. Now let's clear that, and let's select the R group on the other side of the bicyclic core. Note that hydrogens do not contribute to the overall LGFE of the ligand, so their GFE score is going to be 0. And now we can see that this R group contributes about -1.3 kcal per mole. Now let's also select the atoms of the middle core of the ligand along with this linker oxygen. Now, as I go through these atoms, you'll see orange and blue. Note that favorable atomic GFEs are orange and unfavorable atomic GFEs are colored in blue. Now going to the drop-down menu and selecting our ligand again, we can see that the sum for these atoms comes to about -4 kcal per mole. You can see some moderately energetic favorable atoms and 2 unfavorable atoms, but notably, this H-bond acceptor nitrogen contributes about -2.1 kcal per mole, indicating that this atom is key for this ligand's affinity to this protein. So with the SILCS Bio GUI, we can analyze the ligands either docked or pose refined by looking at different FragMaps, also atomic GFEs, and sums of R groups together for designing the next molecule to bring to your lab. That concludes this video tutorial. Thank you for watching and see you next time.